Okay, so this is part 3. I want to talk about sound. Later you will see why. So sound is a propagation of disturbance of an elastic medium, such as air or water. The word propagation means moving through, spreading through. Sound is a way to communicate information or send signals from place to place. You all know that. Now, here's the point. When we talk of the speed of sound, speed relative to what? So what we actually mean is the speed of sound relative to the medium that propagates that disturbance. Okay, so let me put that down. Okay, relative to the medium through which that disturbance propagates. And what controls the speed of sound? The medium does. Okay, the medium through which the disturbance propagates determines how fast that disturbance propagates through it. So once the disturbance has been created by some source, the sound now belongs to the medium. It doesn't belong to you anymore. And the speed of the source is actually irrelevant. Okay. Sorry. So the speed of sound created by a train that's moving or by a train that's stationary is the same, as long as by speed of sound we mean the speed of sound relative to the medium. So here I'm on the ground. Let's say it's not a windy day, so the air is still relative to me, and I'm observing sound emitted by a moving train, and I see sound waves. They move at 340 meters per second relative to me. Okay, now I observe a sound emitted by a stationary train, and those sound waves also move at 340 meters per second relative to me, or relative to the medium, assuming I'm stationary relative to the medium. Okay, once the sound has been created, it moves through the medium with a speed set by the medium. Okay, I think I've belabored this point enough. So in a sense, when we talk about sound, we actually introduce a special reference frame, the frame of the medium. Okay, now I would like to consider the following scenario. Okay, so let me move this a little bit. There's a road, and there is a convertible car. Okay, a very ugly convertible car, but that doesn't matter for the present purpose. Okay, in the middle of the car, there's a speaker. Okay, and that speaker emits some kind of a pulse or beep or clap, some kind of a disturbance, and it spreads out in all directions. In this case, I just drew front and back. Okay, that's the only thing that matters. Okay, now at the front and rear bumper, there are sound detectors. Okay, so detector 1 and detector 2. Okay, so this is a sound emitter. Okay, and this is a sound detector. Okay, this is the front detector, and this is the back detector. Okay. And this is the front. Back sound detector, front sound detector. Okay. My question is, do both of these detectors register the pulse at the same time? What do you think? The car is moving. Let's say the air is still relative to the ground. Let's say it's not a windy day. Okay. Air is still relative to the ground. Okay. So if you said no, that the sound does not arrive to the front and back detector simultaneously, you're correct. Okay, why? Because the pulse moves at some speed relative to the medium. Okay, let's say the medium is air and it's stationary relative to the ground, but the front detector runs away from the pulse that's moving towards it, while the back detector runs towards the pulse, right? So, so if this is sound, it's moving to the front detector, but the front detector is running away from it. Remember, once the sound has been created, it belongs to the medium. Okay, so you have basically a sound that's moving with some speed of sound relative to the medium, and the front detector is moving with some other speed. Okay, so this is they're moving with different speeds, and so the pulse that's about to arrive to the front, it's trying to catch up with the front detector. But the pulse that's moving towards the back, okay, it's going towards the detector. Okay, so you see these guys are going towards each other, these guys are going away from each other. And probably the speed of sound is faster than the speed of the car. Okay, so that's the qualitative idea. So clearly the sound does not arrive simultaneously to both front and end. You will see that this is kind of a big deal once we start doing Einsteinian relativity. So now let's do a quantitative analysis, okay? And we will do it from the perspective of two frames. Frame S, the frame of the ground, or which is the same as the frame of the medium, because the medium is still relative to the ground, and frame S prime, the frame of the car, okay? So here's the frame of the ground, S, ground frame, X and Y, and I guess here's S prime, S prime, I prime. Okay, so this is a okay, the usual scenario. So let me give you some data. Let's say the length of the car is L. Okay? Length of the car is L. The speed of sound relative to the air is S. Speed. And the speed of the car relative to the ground, and thus relative to the air, is V. Okay? Okay. So how do we set it up? So let's first do the analysis from the ground. Okay? Analysis from frame S. So during time interval delta t front, the time that it takes for the forward pulse to catch up to the detector, the car itself will have moved the distance, a certain distance. Okay, so during delta t front, time to time for the pulse to reach the front detector, the car, how far does it move? V times delta t, right? Moves V times delta t front. Okay? So what's the total distance that the forward moving pulse has to travel? Travels a distance. Well, if the car wasn't moving, it would travel L over 2 because the sound emitter is in the middle. Okay, so this is, let's say that this is L over 2, and this is also L over 2. The drawing maybe doesn't represent it, but it's in the middle of the car. The sound emitter is in the middle of the car. So if the car wasn't moving, it would travel a distance L over 2. But because the sound is moving, it has to travel an extra distance by which the front detector has moved during that time. So it travels a distance L over 2 plus extra bit. It has to work harder, it has to move further. The extra bit by which the front detector itself has moved. Okay? On the other hand, the pulse moves with speed s. Okay? So it travels a distance s times delta tf. Okay? On the other hand, the pulse moves with speed s over time delta t front, right? That's the time to reach the front. So it moves a distance s times delta t front. Okay. So these are two expressions for how far the pulse has moved. They're just different ways to express it. So we equate them, L over 2 plus V times delta T F equals S times delta T F. And we solve for delta T F. We find that the time required to catch up to the front detector is L over 2, just doing some algebra, S minus. Okay? So you can see right away that if the car moves with speed s or faster, the pulse will never arrive to the front detector. Okay, does that make sense? Well, if the pulse moves relative to the medium with the same speed that the car moves relative to the medium, it will never catch up. So if s equals v, the denominator becomes 0. So something over 0 is infinite. It will take infinite amount of time. That makes sense. And it's somewhat similar to problem 2 on your homework. Okay. What about the backward moving pulse? Okay. The distance that the backward moving pulse has to travel, if the car wasn't moving, it's L over 2, but because it's moving, it has to travel less because the back detector is approaching that pulse. So pulse has to travel less. The pulse travels a distance L over 2 minus v times delta t back. Okay, so this is the time. So it takes time delta t back. Okay. Time delta t back. Okay, so that's on the one hand. On the other hand, it's moving with speed s over duration delta t back. So the pulse moves a distance distance s times delta t back. Again, these are two expressions for how far the back moving pulse travels until it meets the back detector. And again, this is all the analysis from the perspective of the ground. So let's say I lay out rulers everywhere, okay, and somehow I can measure the location in space where the pulse was emitted and the location in space where the front pulse caught up to the front detector and where the back moving pulse caught up to the back detector. So I can really measure those distances, okay? So again, I equate, so I have L over 2 minus V times delta T back equals L S times delta T back. And when I solve for delta T back, I find the delta T back, the time required for the back pulse to reach the back detector equals L over 2 times S plus C. So several things come out of this. First of all, you can see that this is always less than this. In fact, this can actually be, I'm hoping you can see as I'm showing. This expression, the time to reach the front, can actually become infinite. The time to reach the back can never be infinite. And we, in general, see that the time to reach the back is less than or equal to the time to reach the front. And when is it equal? When the car is not moving. When V is 0, the two expressions become the same. By the way, I hope you understand that this is not a derivation, okay? This is what I would call solving a problem, okay? There is no such thing as derivations. It's kind of it's a misconception that some of you inherited from high school. There's only solving a problem. I want to solve a problem, whether the pulses arrive instantaneously or not, and I want to make it quantitative. What's the difference in time that it takes to arrive, for the pulse to arrive to the front and the pulse to arrive to the back? So it's solving a problem. I'm just doing it with letters. Okay, we've grown up a little bit, so we can work with letters now. So it's not a derivation. So this is the analysis from the frame of the ground. Now it's the analysis of the same quantities, delta T front and delta T back, but analyzed from the car. So let me use the blue ink to be consistent with frame S prime being blue. So analysis from the car's frame S prime. Okay. Actually, it would be ideal if you pause the video right now and you work it out yourself. And then you watch, so you get an instant feedback. Okay, you don't even need me to grade you. You will immediately see whether you're on top of the game or not. So do that. So, okay, I presume you've paused the video, you've wrestled with it. So let's do the analysis from the perspective of the car together. The forward moving pulse travels a distance L over 2. Agree? If I'm in the car, imagine, so I see a pulse, okay, I'm the driver, so here's the pulse emitter, Tick, 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 boom. It reaches the front. How far does it travel? It travels L over 2. Okay, the pulse moves a distance L over 2. Again, distances are not invariant, as we saw, right? S equals, X equals X prime plus VT, remember? So therefore, it's not surprising that in my coordinate system, the coordinate system that's attached to the car, I measure a different amount of space that was taken up by the by how far the pulse had to travel. Okay, but how fast does it travel? How fast does it travel? Its speed, S minus V. Remember, U equals U prime plus V. So U prime is U minus V, except that what I mean by U is the speed of sound. So I call it S here, right? So does that make sense? That this is how fast I think the sound travels. Remember, S is the speed with which the sound travels relative to the medium, relative to frame S, in frame S. Okay? In frame S prime, it moves with a different speed. So you can think of this as just an example of using Galilean velocity transformation. I guess you can also think of this as sound being blown back by the wind. I don't really like that, but you can think of it that way if it helps you to visualize it. Does it make sense? Well, if S equals V, the sound is trying to move a certain distance and the car moves the same distance over that period of time. So if the car moves at the speed of sound, the pulse will just linger at the speaker. Remember, it's a convertible, right? So there's an ambient medium and the sound propagates through that ambient medium with that speed. That's why we're working with a convertible. Okay, so if the car moves at the speed of sound is set by the surrounding medium, and the car is cutting through that medium with a certain speed, then the pulse will just linger at the speaker. Okay, that's known as a shock wave, because if it's a continuously emitted wave, it will be piling up at the speaker, and that's what a shock wave is. Okay, so so therefore, L over 2, the distance that the front pulse moves, equals S minus V times delta T front. And we find that delta T front equals L over 2 S minus V. This is a 2. Okay? And similarly, the backward moving pulse moves a distance as L over 2 from the middle of the car to the back bumper, but with what speed? With speed S plus V. Okay? That makes sense because the car is moving this way, the pulse is moving that way. So from the perspective of the car, it looks like the pulse is moving back even faster. That's where the plus comes from. When all the dust settles, you would find that the time for the backward moving pulse to move from the emitter to the back receiver is L over 2 S plus V. Okay? So first of all, the answers agree. So these two answers are the same as what we found when doing the analysis from the perspective of the ground frame. And also, where the agreement is not just in the value of the answers. If you plug in the numbers, you would get the same numerical values, but they agree, both the observers on the ground and the observers on the car, both agree on the fact that the events, the two events, when the pulse hits the front detector and when the pulse hits the back detector, that these events are non-simultaneous. Both observers agree that the two events are non-simultaneous. We will see a stark difference between this and what happens with light. Okay, so that's why we're doing this exercise. By the way, what do I mean by observers agree? After all, the only observers that matter are the two microphones that receive the sound detector. Yes, but we can also plant microphones all along the ground. So imagine Freeway 101 with microphones densely packed all along the curb. It's like a continuous microphone curb line. At the moment when the pulse has arrived to the front bumper, there's a microphone sitting on the ground that registers that event at that spot where the sound has caught up with the front bumper. Similar for the rear bumper. So that's what it means to say that this event is seen from the ground. Oftentimes when people begin studying relativity, they start to think, oh, well, if there's an observer from the ground, there's a time delay for that observer to find out about an event. No. That observer has placed a continuum of his friends. He has infinite number of friends or microphones. And that observer has placed all of these helpers all along the road. So when something happens, it happens at position of one of those detectors, boom. Okay? So you can tell exactly the time when that happens in one reference frame, and then people in the other reference frame, they can do the same. Okay? So imagine that the ground observers, they have put rulers and clocks everywhere along the ground, and they have synchronized those clocks. And the observers in the car, they have lined their car and put clocks everywhere along the car. Right? So it's like rulers and clocks moving. Okay? And they synchronize their clocks. So that's what we mean when we talk about observation as seen from different reference frames. Okay, so I guess I should write this down. I'm going to use a red ink for that. So it's a little bit like this. So you have, let's say this is frame S. You place a ruler, and at every point you place a clock. So when an event happens, it's like a continuum of clocks. And of course you synchronize them. So when there's some event happens, boom, it happens right here at such and such a time. Okay, and this procedure eliminates having to worry about time delays associated with different observers. There are no time delays. Okay, there are, but we want to eliminate that triviality. Okay, and so by doing this, we eliminate time delays. Time delay is only when there's a single person, single observer. But with this method, we eliminate having to worry about time delays. That's what I mean by it. There are, but we don't worry about it. We don't worry about it because when you make a measurement like this, there are no time delays. That's what I mean. Okay. So to judge, so the event when the pulse arrives to each bumper, seen from the ground in this strange setup, will be judged as non-simultaneously in accordance with this procedure. And the event when the pulse arrives to each bumper, as seen from the car, will also be judged to be non-simultaneous. Okay. So to judge simultaneity, we can endow each microphone with a clock, and we can synchronize these clocks, like I said, as well. We can synchronize all the clocks in each frame, clocks at the microphones, clocks at the emitter, and do this procedure. The conclusion that the events are non-simultaneous is important. The reason why observers in both frames agree on non-simultaneity of the detection events is that sound propagates with a fixed speed relative to the medium. There's a special reference frame in this experiment, the frame of the medium. And both observers measure the speed of sound relative to that one and the same frame. Let's keep that in mind.